Let's see if we can understand the very basic physics of the greenhouse effect by using a simple model. Our simple model begins with a simplifying premise, that is, the atmosphere is completely transparent to solar radiation. We'll also make another simplifying premise that the atmosphere is completely opaque to terrestrial or infrared radiation. And we'll consider that the atmosphere is a single slab of gas emitting at a single temperature. So in this simple model, infrared emission is from the surface of the planet and the atmosphere. Here is a sketch of what this model looks like. We have a single layer of gas represented by temperature T sub A. We have a solid or liquid surface whose surface temperature is T sub S. Incoming sunlight is represented by this stream of radiation, whose magnitude is given by the Stefan-Boltzmann constant times TE to the fourth power. Remember what this is, by definition, is the solar constant divided by 4 times 1 minus the planetary albedo. So this is the net sunlight coming into the planet after we subtract out the portion that's reflected. These arrows represent infrared radiation emitted by the atmosphere. The atmosphere radiates energy both upward and downward, again by Stefan-Boltzmann, at the rate sigma times the atmospheric temperature raised to the fourth power. And finally, we have infrared radiation emitted by the surface at sigma Ts to the fourth. Let's see if we can calculate what the atmospheric temperature and the surface temperature is in this very simple model, given the amount of sunlight as represented by the effective emission temperature of the planet T sub E, which remember is about 255 Kelvin. Well, the first thing that we would recognize is that in balance, we have to have the same amount of radiation leaving the system, sigma Ta to the fourth, as we have entering the system, sigma Te to the fourth. This tells us that the atmospheric temperature in this very simple model is equal to the effective emission temperature of the planet. So we've already found that the temperature of the atmosphere in this simple model is 255 degrees Kelvin, the effective emission temperature of the planet. What about the surface? Well, let's look at the energy balance of the surface. It's emitting infrared radiation at sigma Ts to the fourth. It's receiving energy from two sources. First of all is sunlight, sigma Te to the fourth. Secondly, back radiation from the atmosphere at the rate sigma Ta to the fourth. So if we have energy balance, the amount of energy emitted by the surface, sigma Ts to the fourth, must equal the amount absorbed from the sun, sigma Te to the fourth, plus the amount transmitted downward from the atmosphere, sigma Ta to the fourth. But we just discovered that T sub A is equal to T sub E, so sigma Ts to the fourth is twice sigma Te to the fourth. And this represents, in stark numbers, the essence of the greenhouse effect. That is, that the surface has to get warm enough not simply to balance the incoming sunlight, but also to balance the amount of radiation coming back from the atmosphere. In this simple model, the amount of radiation coming down from the atmosphere is equal to the amount of radiation coming in from the sun. So that gives you a factor of 2, twice as much energy being received by the surface as in the case that the Earth had no atmosphere at all. So in this model, the surface receives as much radiation from the atmosphere as it does directly from the sun. In radiative equilibrium, then, once again to review this, the temperature of the atmosphere is equal to the effective emission temperature. And the surface energy balance tells us that sigma Ts to the fourth is twice sigma Te to the fourth, which means that the surface temperature is 2 to the 1/4 power times Te, which is 303 degrees Kelvin, about 30 degrees centigrade. Well, that's actually somewhat warmer than we observe it to be. The surface temperature in this model is too large because of some of the simplifying approximations we've made. First of all, the real atmosphere is not completely opaque either to solar or infrared radiation. And very importantly, we've neglected here another way of transmitting energy through the atmosphere, and that is by convection. It's not just radiation that's moving heat around. We're going to talk about convection more extensively later in the course.